Hello, everyone. Welcome. Thank you for joining our diagnostic training session this evening. Now, if you have any questions throughout the program, if you're watching us on Zoom, just make sure you put them in the Q&A box. You look on the top or bottom of your screen, wherever you see the Zoom controls, you can click on the little Q&A button. Should open another window. You can type in your question, hit submit, and I'll get to them at the end of the program. If you're watching us live on YouTube, you can use the live chat and ask any questions there, and I'll be sure to get to those as well at the end. If you're watching this on YouTube, not live, the live chat function wouldn't be there. So don't worry about that. Just maybe leave a comment. With that, my name is Jason Gabrinas. I am one of Snap-on's national diagnostic technical trainers. Been with the training department the last 7 years, traveling around North America, helping technicians and shop owners get the most out of their diagnostic equipment. Before that, it was a couple years as a diagnostic sales rep with Snap-on. So I had 30 different Snap-on franchisees I worked with, as well as the shops that they serviced in order to help everyone get the most out of their diagnostic needs. Before that, 8 years at Subaru. So I was a dealership technician at Subaru. And over time became the default diagnostic guy in the shop, right? So I was always the one that got the drivability problems, the intermittent issues, the weird wiring problems that would seem to crop up on those cars, always seemed to find their way into my bay. So that's really where I cut my diagnostic teeth, was trying to figure out those strange head scratcher type problems that would come in. And before that, a bunch of other miscellaneous wrenching jobs. Been about 25 years under the hood experience for me. So our topic today is data bus testing and diagnosis. And this is actually part one of a two-part course. So if you are with us this week, this is part one. And then next week will be part two. So we'll just continue on through our discussion next week. So for this week, we're going to do a high-level overview of networking and what all network does and what a network is. And we'll talk through mainly our low-speed networks. So let's say J1850, both variable pulse width and pulse width modulated styles, K-line, LIN Bus, and CAN. And then next week, we'll expand upon that and we'll go into FlexRay, most, and talk a little bit about Ethernet or diagnostics over IP. So for this week, focusing on the first three. Next week, as I said, we'll expand and go to the next three. So a network. What is a network? Let's get down to basics here. So a network is a system that utilizes information through all available resources. So anything on that network. In the case of a vehicle, all of the modules attached to each other are able to communicate with each other. Now, there are some networks out there you might have already heard of, you might already know, such as LAN. So LAN, it stands for Local Area Network. That is a bunch of computers hooked up to basically the same router, right? So that's like in your shop. Just think about your shop or your house. All of the machines, all the computers and phones and whatnot, all hooked up to that same router. That'd be a local area network. And then we have WAN or WAN, which would be wide area network. So that is a bunch of LANs connected together over a network. So that's really just a fancy way of describing the internet. All right, so multiple smaller networks all merged into one larger network. And then the types of networks that we're talking about in the automotive industry, there's more than, of course, listed on the screen, but a few of the more popular ones, and of course, we know there's a ton of acronyms, so we want to talk through that, is CAN. So CAN stands for Controller Area Network. LIN stands for Local Interconnect Network. And then DOIP, which is one of the fairly newer terms that are out there, that's Diagnostics Over IP. So that is using Ethernet protocol, like on home computers, in order to do diagnosis on a vehicle, as well as communicate through networks on a vehicle. And when we're talking about a network, what it really boils down to is a voltage differential. There's a high level to the voltage and a low level to the voltage. The voltage field in between there, the difference between the high and the low, is what we call our voltage differential. Different networks work with different voltage differentials and different high levels and different low levels. So it's just good to be aware of what kind of signal am I looking for. Do I need to see a 12-volt signal? Do I need to see a 5-volt signal? Do I need to see a 7-volt signal? Or is it something completely different, not just a single wave, square wave? So there's just an example right here of a waveform. This is a LIN bus. We'll talk a little bit more about that as we go on. But the voltage differential on this LIN bus should be around about 12 volts because LIN bus uses a 12-volt differential. So we'll see at the high side here, and all it is just a square wave, right? It makes different varying lengths of time on a square wave, and this represents the different bits and bytes of data that go back and forth between a computer. So this one's normally on the high side, and then it pulls down to ground in order to communicate and send data. So on my high side, I'm looking at 13.35 volts. So that's whatever alternator voltage was at the time. And then it pulls down to 0.91 volts. So not even, it's almost a volt even. So that's 2.44 volts. If we do the math in between there, take our delta time, 2.44 volts in that field there. That's within a few tenths of a volt of that 12 volts. That's within an expected range of where we'd want to be. In this case, we want to pretty much just anywhere over 12 volts and then have a 12 volt range in between. If we were seeing maybe 6, 7, 8, 5 volts, that would be considered an error on this type of network, right? So we want to worry about that voltage differential. We'll compare it between the different types of networks. When it comes to testing networks, the easiest way to access and probably the most common way to access would be through the data link connector, right? It's right under the dash, easy enough to get to. And there are some standardized positions for these network wires. So pin 1, for example, low speed CAN communications. So I know GM for many of their newer cars, they actually have a single wire low speed CAN, and that's almost always on pin 1. Pin 2, J1850 variable pulse width would be a single wire protocol that, once again, GM used mid-90s through the mid-2000s there. So that's a single wire protocol. Or that would also be if I had a J1850 pulse width modulated signal, positive side, that would be on that pin as well. And we'll talk through the different networks as we go, as I said. Pins 4 and 5 on my DLC, my 16-pin DLC, are always going to be ground. So pin 4 is a scan tool power ground. Pin 5 is a common signal ground. So if you need to find a known good ground, hopefully you would have a known good ground at there. But that's a good thing to tap into right there. Pin 6 and 14. So that would be here and here. Pin 6 and 14 opposite of each other. That would be a general CAN bus. So the main CAN bus on a vehicle, that's the standardized place for those pins. Pin 7, that we're getting into another single wire protocol, the K line. So keyword communications. So that's on pin 7. Also with the K line, we can also have what we call an L line down here on pin 15. So that's used for, it's optional. It's not always on every car with that, but that's used for waking up modules. So it'll send a wake up signal out and wake up the modules. Pin 16 is always power. And then the other pins here denoted in white can be used by manufacturers at their discretion. So for example, I know we did a research project on it was like 2013 Cadillac, and they had their normal CAN bus here and here, 6 and 14. They also had another CAN bus on let's see, the 12 and 13, and then also on 3 and 11. So they had 3 CAN buses across this vehicle. Because of the amount of modules on that car, they split up the networks into multiple pins on that DLC. So really, if you want to find a communication problem, first off, you need to go through a wiring diagram and see where would I find what modules on what wire, right? So you need to be able to go through that. So that is our standardized diagnostic link connector. They're using almost every single pin on there at this point. It used to just be, maybe power, 2 grounds, and then J1850. So that's what, four pins. And now we're using almost all of them. So we've come a long way as far as network complexity on the cars, right? So that's why we do these classes, right? Good way to get into the diagnostic connector as well, so without damaging anything. So we don't want a front probe, because that could spread out the terminals. That would cause a communication problem, perhaps. It's usually pretty hard to back probe there, right? Because they're underneath the dash somewhere and pretty hard to get to normally. So a good way to do that is to use some form of a breakout box. This is the Blue Point brand right there. It's got a short cable, plugs into the DLC. On the other side of the box is another DLC where you can hook up your scan tool. And then it has 16 of these banana jacks where we can tap in and get a signal. So in this case, we're just doing power and ground, 16 and 4, right? But if I wanted to do CAN, I could do 6 and 14, right? And they could just tap in there. And you can also communicate with the vehicle at the same time as you're reading that signal. And oftentimes, you won't get a signal until the vehicle starts communicating. It'll often just sit there at idle and not transmit any data until you call for data from the vehicle. So what I like to do when I don't see communication on there is I'll just go into a data PID list and just have it send data to the scan tool. That way we can see the back and forth between the module and the scan tool. So let's talk about low speed networks. start at the bottom and I guess work our way up in speed, right? So we'll start with J1850. That's a fairly common one. Like I said, back mid-90s through mid-2000s. GM was a big fan of this. They used it on very many of their vehicles. J1850 VPW, which stands for variable pulse width. So it varies the pulse width in order to transmit the signals. That bus consists of a single wire with a transmission rate of 10.417 kilobits per second, if you need to know down to the hundredth of the kilobit, right? It uses a 7-volt differential. So what we should see when everything's communicating correctly is a 7-volt square wave going across the screen. J1850 pulse width modulated bus is a 2-wire version of that. So it's actually a higher speed transmission or higher transmission rate, 41.6 kilobits per second. So considerably faster, about 4 times faster than what the single wire is. This was pretty common on Fords of the same era. So around about OBD-II through mid 2000s when they went to CAN. So in this case, they use about a 5-volt differential on my data. So here's an example on a variable pulse width. So that is a single wire GM class 2 data bus, they call it. So that's on pin 2 on my DLC there. And we see it's just a 7-volt roughly square wave right there. And then here's an example on J1850 pulse width modulated off of Ford. You'll notice that there's 2 channels because I said we had a positive and a negative, right? And then it's about an every other data bit goes up and down, either higher or lower than the others. And they pretty much mirror each other on both sides. So you see you have a larger packet there, a smaller packet there. In this case, on the smaller packet, pin high side's going to 4.5, low side's going to 0.55, so that's about 4 volts in there. And then on this one with the bigger packet there, it's 0.22 to 5.04, so that's almost 5 volts there, right? So there's your difference in between the different data packets. You can see how a known good would look in that case. Then other vehicles round about that same era would use K-line. So K-line is just on a different pin, and it's another single wire bus, and it transmits at a rate of 10.65 kilobits per second. So it's a little bit faster than the J1850, but it's still fairly slow in the grand scheme of things. K-line uses a 10 to 12 volt differential. I've seen some with 10 volts, some with 12 volts. And I'll tell you what, on Subarus, since I have experience with Subarus, right? Subaru used K-line all the way up to like 2014 for their scan tool. So if you've ever noticed maybe data collection on some Subarus might not be as fast as you like, that's why, because they use that K-line protocol, which is slower than any of the other protocols they could be using, such as CAN. So there's about 10 volts there on the top, and there's about 0 volts there on the bottom. So there's my data packet right there. So my high side, my low side. There's my different bits and bytes of data as we go. Now let's talk about LIN Bus. So LIN Bus is newer, I guess you could say, on the scene. LIN stands for Local Interconnect Network, and it was specially developed to achieve cost-effective communications for intelligent sensors and actuators in motor vehicles. It requires a master controller and a slave controller. So we have one telling something else what to do. So usually like a switch in a motor or something of that nature. It's used wherever the bandwidth and versatility of CAN are not needed. So CAN is a considerably more higher speed. It has more bandwidth. It's able to transmit more data. With LIN, we don't need to transmit that much data on there. It's more of an on or off type situation. With CAN, it's sending speed sensors and temperature sensors and all that information around the modules on the vehicles. So LIN is really used for a lot of like your body type communication. So it's, once again, it's a single wire, and it has a transmission rate of up to 20 kilobits per second. So once again, we don't need to drive the car with a LIN bus. We need to turn things on and off with a LIN bus. So that's why it doesn't need to be that fast. It just needs to be fast enough for a human being to notice when it happens, right? So LIN uses a 12 volt differential, as we had mentioned earlier on when we saw that first slide there. So things that we would use LIN on: sunroof controls, lighting controls, steering wheel. Pretty much most vehicles nowadays, any of the button on the steering wheel, and there can be a lot of buttons on a steering wheel now, those are often LIN. Seat motors, occupant sensors, control panels for the seats, engine sensors, and small motors, just the inconsequential stuff that not really the throttle or anything of that nature, but smaller things. Grill shutters, active grill shutters are pretty common nowadays. Climate control, my blend door actuators, etc. How about doors, mirrors, mirror switches, window lift motors? How about wipers? And if you were with us last week and we talked about that there was a 2016 Tahoe for the body control module for the rear wiper, well, that control for a rear wiper on that vehicle from the module to the motor is just one LIN wire. The LIN sends the signal out and it says, okay, turn on. All right, so that is a type of LIN bus that we would use. So as I said, many body electrical things is the majority of those. And then here's just another example of that LIN bus signal. High side of 13 volts, low side of 9/10 of a volt. We have about a 12-volt differential in there, and that's close enough, right? So that is all of our single wire networks we're going to talk about. Now let's just scratch the surface or get started with our 2-wire networks. So we'll start with CAN. Because once we learn CAN, we can apply it to most of the other 2-wire networks because they're very similar in how they operate. So high-speed CAN consists of 2 twisted wires with a transmission rate of around 100 to 500 kilobits per second. That's a pretty good swing there. So when you get down in maybe the 100 range, you'd be thinking maybe you could call that mid-speed CAN because you may have heard of that before. And then higher speed CAN's 500 kilobits. When we get up faster than that, we're talking about maybe some other different technologies such as FlexRay, which we're going to talk about next week. So CAN uses about a 2 to a 2.5 volt differential. As we look at the way the picture looks, the data packets, we'll see where we get that 2 to 2.5 volt differential. One signal circuit is called CAN high, and the other one is called CAN low. So we actually have 2, as we said, twisted wires. And by the way, it is important to keep those wires twisted. If you ever have a problem and you're taking things apart and testing things, you want to leave those wires twisted up because that's good for rejecting RF noise, right? That's why they're twisted together, to reject the noise. Now, at each end of the data bus, there's a 120 ohm resistor at the end of any line on the CAN bus. So I know I've seen vehicles where they have just like an open spot for an optional controller that's not equipped on this vehicle, and they just plug in a little resistor wire in there just to tell it, hey, here's the end of the line. We don't need to have any more data past that point. It's basically what that 120 ohm resistor does for us. So here's a simplified graphic of a CAN bus. So we have CAN high, as we said, that terminates on DLC pin 6, and then DLC pin 14 terminates with CAN low. More often than not, that 120 ohm resistor we talked about across the end of the wires, that'll be inside a controller. And more often than not, if you have a CAN problem, more often than not, it's a controller. The thing about CAN is it is a mesh network, so everything is connected to everything else. It's also fairly modular, so we can expand as we go. So we can add a few modules on there, and they'll start communicating, transmitting data back and forth. You want to add some more modules? Sure, let's add some more modules. Just plug in a couple more. As I said, we could have those optional plugs, right? And then even if we have a single module on there, it can still use that CAN protocol to talk to the scan tool, right? So we can actually get data out of a lone single module on a CAN bus network. So it all works. It's fairly, I don't want to say it's that complex, but it is definitely more complex than the single wire networks we were talking about before. And the messages are different and the patterns are different. But if you know how to diagnose this, it'll help you diagnose any of the other 2-wire modules. So here's an example, high-speed CAN, known good here. And we'll talk a little bit more in depth about the voltages and what we see here in a few minutes when we go live on the tool. But we want to see a flat line here, which is our idle voltage, and then these data packets are the square waves here. And what you're actually seeing on this 2-wire is you're seeing a round trip. So this side goes out, this side comes in, right? So it's kind of like a transmit and receive. And then all the modules have clocks inside them, like crystal clocks. And they can change the timing of those packets so they line up, right? So we want to make sure they line up. We want to make sure they're even on either side. And as I said, we'll talk about that a little further in a couple of minutes. And that's on pin 6 and 14 for the main network on the DLC. We have these various networks on a vehicle. Are they able to communicate with each other? Can they communicate with each other? Well, in order to do that, yes, we can. So we would use what we call a gateway module to translate the data from, say, a high-speed network to a low-speed single-wire network on a vehicle if we needed to have that happen. Think about it like a router. Right? So you have your Wi-Fi router at your shop or at your house, and it routes the signals wherever it particularly needs to go. right? So I could have hardline, I could have Wi-Fi and out in the shop, right? So it just routes the signals. Oftentimes on a car, it could be called a gateway module. Oftentimes on a car, it might not be called a gateway module. It could be in some other sort of module on the vehicle. I think of like signal acquisition module on a Mercedes. That works often in that type of way. Body control module oftentimes can be your gateway module as well to translate those signals between all of them. Let's use just a sample scenario, for example. So I have a little wiring diagram here. And let's say on this vehicle, this is a Chevy, I think it was a Malibu. We have a technician that can't communicate with the vehicle. So they go in, they try to scan the engine for codes, and they can't communicate with the engine module. So they suspect that there's a problem with the scan tool. Well, oftentimes, more often than not, it's probably not the scan tool's fault. It's probably the car's fault, right? Because if we think about it, why is the car in the shop in the first place? It's probably because there's a problem, right? So if you ever run into that situation, we were trying to scan one module at a time. The best way to avoid that is to maybe do that pre-scan on the vehicle where we scan all the modules and see what we have for communication. But that's also a good way to check for communication. Because if, say, I didn't have communication with the engine, the transmission, the body control module, the brake module, etc., but I did have communication with, say, like the radio and the SRS module and maybe the instrument cluster, I could communicate with half the car and not the other half of the car. That's where you might suspect a gateway module is the problem. So if we look at this wiring diagram I have on the screen, on the left-hand side, that is the DLC. All right, we got pin 16's power, pin 4 and 5 are ground. Looks like on this one, it also has CAN, so that's pin 6 and 14, as we said before. And for those pins 6 and 14, they go right into the body control module. And then pin 1 is their low-speed single wire network, and that also goes into the body control module. All right, so all signals go to the body control module before it goes out to the rest of the vehicle. So that means that is my gateway module. And we see we have just the 2 wires on the CAN go out to the high-speed portion of the car. Well, maybe it's not translating, and maybe there's some sort of an error on this part of the computer, because I can communicate with the rest of the vehicle on these green boxes. I just can't communicate with anything in this high-speed area, right? So that would be the body control module. So in this case, it was the body control module. They replaced it, and communication was restored with the vehicle with all modules. So it's just the body control module was not letting the signal pass for the high-speed side. So speaking of errors and problems, what kind of problems can we have, and what would that look like? Because you can't always get a known bad pattern, right? But in this case, we do have at least one known bad pattern. So this is on a single bus, or single wire bus, J1850 bus. And we can see it's 7 volts on the top. And as we learned earlier, this should be a square wave, right? We should have a flat top and a flat bottom, but we don't. We also have 7 volts here, and then it pulls down to ground in order to send a signal. So ground is here, that's 0 volts. Notice how the bottom is not always making it to ground. Over here it did. Over here it made it down to ground, but it took a long time to get there. If you ever see a pattern on a scope and you want it, it's supposed to be a square wave, like coming down nice and straight and then over, and you see it curve like this instead on the leading edge, that indicates high resistance on the ground side. So it's not pulling it down to ground fast enough. So if we think about what a scope is, it's basically just a voltage over a time, right? Or a signal over a time. So if I am coming straight down, that is a very short amount of time to get from 7 volts to 0. If I'm coming down in a curve like that, though, that means it's taking a long time because horizontal is the time. So that horizontal measurement is the time. So if it came down nice and straight, that's very fast. That's a short amount of time. This is taking a long amount of time to get down to ground. Over here, it didn't even make it to ground. It was like 0.69 volts. All right, so it didn't even make it to ground over there. So that is an indicator of a problem on the ground side of the circuit. So how would we test this vehicle? Well, first off, we take out the, we would have maybe a communication issue first off. Second off, we would probably go and pull a wiring diagram. Would be a good thing to do. So we have a wiring diagram here. On this vehicle, it was a GMC truck. And on this vehicle, it used a single wire protocol off pin 2 there. And also on this vehicle, and it's not just GMs, many vehicles have this style of network. They call it a star style of network. So each module has a single wire that goes to a central point. In this case, they call it a splice pack, or GM might also call it a star connector. So that is where all the modules will link up in this one connector. And then there's a shorting bar that goes in there that shorts all the modules together so they can communicate. And then it goes over to the DLC as well. If any of these modules go down, it could pull other modules down as well, or maybe a group of modules if we have a problem, say, over there. All right, so we can go through and we can test that and see by disconnecting modules. This gives us a test point under the dash. So there's just an example of what the connector would look like. There's that shorting bar right there. All you have to do is pop this out. It's attached to one of the main harnesses on the vehicle, and it's just straight across. It's 12 pins. Now, what we could do is we could do jumper wires. If you've worked through the flow chart on one of these cars, it says use jumper wires or paper clips, that sort of thing, to check for communication between the modules. So you put one wire where the DLC comes in, and then you'll go to the ECM, then you'll go to the TCM, et cetera, et cetera, et cetera, and see how the network performs. We also have an automated tool that can do that for us as well. Now, it's designed to work with GMs. It has the two main GM connectors that come with it, but it also has a universal connector that comes with 12 pins that can connect in many other manufacturer vehicles. Many vehicles have this style on there. And what it does is called the data bus fault finder. Now, I also hear these might be getting a little hard to find out there, but if you do have one, or if you were able to get one, it plugs in to that same cable there. It scans the whole bus and checks, do I have connectivity to the module? And is that module shorted to power or ground? So in this case, we have these pins here. Need to be on the right screen there, and then back up. All right, so we have these lights, which indicate that it's connected to the module. And then we have this one shorted to ground, or that one shorted to power. So this module's to ground, that module's to ground, that module's to ground, and the bus overall is also shorted to ground. It takes like 10 seconds to figure this out. Then we also have these buttons on here. And these buttons will take that module out of the circuit and see if the pattern changes. So if I take a module out of the circuit, pattern gets back to normal, then I know that module is connected to whatever pin that is, D or F or H, whatever it happens to be. That's the problem, right? So you just go one at a time, turn it off, does it get better, turn it back on, turn it off, does it get better, until it does. Now, you could also do that manually. If you didn't have access to one of these tools, you could do it manually just by find the module under the dash, unplug the network connector, see if the pattern resolves itself. If it does, then you know that's your bad module. If it doesn't, then you move on to the next one. You can also use that splice pack underneath to check if it's set up in that way. So we would go through, and then here is a normal look for a single wire bus. We have a square wave, nice and square. It's not having those strange ground side problems that we were having before. We don't have the curves. We have it kind of nice and straight down. So that's an example of a fixed car. All right, so that is our overview for tonight. We're going to go into live on the tool now. Just going to look through chat here real quick. Looks like YouTube chat looks clear. And Matt is asking me a very long question, so I will get back to you at the end. So we'll take time now. That's a good paragraph there, Matt. So I'll get back to the question at the end. All right, so here is my Zeus, and the best way to find information on networks on any of our tools that have guided component testing. So that'd be anything with a scope, because you do need to use a scope to test the network. As you can see with those pictures on the screen, you really can't test it with a meter. It won't really give you any information as to what's going on. So you do need to go in any of the tools of the guided component test. So Zeus, Varus, Modus, Triton, and Vantage. All right, any of those tools will have the guided component test. We can click on that. And once we load in there, we have this little secret that's been in here for a while. But we have built-in training and classes on scope use, guided component testing use, etc. So we go in here, and I go into the how-to section. There are 65 different categories of class. 10-minute classes, 15-minute classes, 20-minute classes. Under each category, there's generally at least 2 or 3 or more classes. So let's say, for example, well, I went to that class the other night, and I learned about that LIN Bus stuff, but I didn't quite remember all of it. So right here, 10-minute LIN Bus class. You can walk through here, and it tells you all about LIN Bus and how it works, and how we have a a 12 volt here, and we have a 0 volt there, and we should see a square wave like that, recessive and dominant when it's transmitting or not. And if we come down here, it gives me a known good pattern. And if we come down a little further, we even could connect to the vehicle and then click view meter, and it'll turn the meter on, set the voltage where it needs to be, sets the time where it needs to be. And then that gives us, you know, the information very easily in that case. So that's LIN Bus. If we go down a little further down, I think the 20-minute classes, we have CAN bus. There are multiple CAN bus classes. If you wanted to go basics and fundamentals, bus arbitration, if you care about learning about that, CAN voltages, error handling, signal quality. How about waveforms? Waveforms is actually a known good and bad waveform library in here for CAN, for generalized CAN overall. So we see here we have this a good one. This one's with the low signal open. This one's with the high signal open. This one's with the low side shorted positive, shorted to power. Could also look like this depending on where we are on the circuit. There's high side shorted to power. And then we have low signal short to ground. Could be shorted to ground here because the high side can still communicate if the low side shorts to ground and vice versa. So we might see a little bit different activity there. Let's see, CAN high signal short to ground and so on and so forth. Oh, and here's where they're shorted together. They are actually, they look identical to each other. They both use the same. So these are shorted together by themselves. So we could come down here and once again hook up to where it says, so pin 6, pin 14, black to ground. And I actually have this hooked up to a CAN bus so we can see what that looks like. And there's my signal on the screen. So you can see that it automatically sets the voltage to 5 volts because we know the range should be within that 5 volt range. And then it also sets up our time to about 200 microseconds. I can slide this over here if I would like to. Make it a little easier to see. And there is my CAN bus signaling on this vehicle. It's a BMW simulation. Now, you may notice something a little bit different about this particular pattern versus what we've been looking at for CAN before. So we have this extra large bit over on the end here. And some vehicles, not all CAN vehicles, but some CAN vehicles, you will see this. This is what they call an ACK bit or an acknowledgement bit. So that's basically telling other computers on the network, okay, here's all my data, and that's where the data ends. This is the period at the end of my sentence. Right, so I'm done here, and then whatever comes next, it's another module, right? So this is acknowledge that it sent and acknowledge that it received. So that's my acknowledgement bit right there. So you may see that depending on the vehicle. All right, so that is learning a little bit more about networking, and there's multiple other classes in here, you know, battery drain, dynamic steering, et cetera, et cetera. So you could really just go through there and see there's a wealth of knowledge in here. Also, if you wanted to just do a generalized CAN bus test, so to say, we could go into power user tests as well. For a dual channel test, there's one on CAN, there's one on FlexRay as well, which we'll talk about next week. But we go into CAN bus, same thing. This one actually looks like it's off of that BMW. And then we would see that same type of pattern. Now, it's generalized vehicles, if you're not really sure. But another way we could do it, since we have the information in here already, there's over 5 million guided component tests in here, and some of them are for networking. So it's VIN specific, goes back to 1981, covers 28 different makes. So in this case, I have a BMW demo board, so I'll go into BMW. It's a 2012 328i with an N52KP. Come in here. And once I've loaded a vehicle, it'll give me a list of systems. In this case, CAN bus would be considered under the engine system because that's my main network. And then we have CAN bus here. So we can go into component information and take a look. There's a wealth of information in there. I'm not going to read through all of this, but you're more than welcome to, because you can hook up, you can identify any car and you don't have to hook up to it in order to read this information, which is also a nice thing. Looks like in this case, it's also good to go to the ECM sometimes. So CAN low, CAN high tells you the wire colors, tells you where they are assigned as far as pins go. Or we could check it at the DLC as well. If I back up there and I go into my signature test, you see it tells me where to connect my wires, yellow, black, and green. And then it gives me my pin assignments there. Signature test gives me a known good pattern on the screen. And then we can also look at the waveform information, which we're going to talk about right now. So I open the meter. And see, it does give me a little bit different look. It's a little bit wider of a look. So 500 microseconds, that's 500 millionths of a second in width. My height is still set at 5 volts though. So we pull that down a little bit. All right, so I'm going to change this, get in a little bit closer. So we'll change the time down a little bit. Go in here, get the time a little bit closer so we can investigate a little closer. Could go to 200, could go to 100 as well. 100 wouldn't fit the whole set of data on the screen, but that's okay. But we'll just leave it like that. All right, I like putting them on top of each other so they're close. Okay, so let's turn on my cursors and see what we get for information. What do we have for voltages? So when it comes to CAN, okay, I didn't click that by accident. All right. So when it comes to CAN, there are set voltages that we're going to use in order to verify whether or not the network's working properly. So you see we have two states. We have our recessive or idle state, and then we have our dominant or transmitting state. So we have either it's not transmitting data or it is transmitting data. As we said before, these squares are the data packets. So CAN high, we have CAN low. When you're connected to a vehicle and it has CAN, if it was known good, we have 2.5 volts in the idle state. So any of these flat spots in between the data bits should also be this level. So we should see round about 2.5 volts. So in this case, 2.369, 2.373. Then when it transmits data, the high side goes up. Anywhere from 1 volt to 1.25 volts is normal expected range. So if I see 1 volt, it's good. If I see a 1.10, we're good. If I see 1.25 volts, we're good. It should go down on the low side by the same amount. So it looks like we have goes up to 3.275 down to 1.404. Difference between those is 0.906 and 0.969. That is pretty darn close. Right, it's really close to 1 volt on both sides. That's within the margin of error. So we're good there. We want to see nice flat tops. We want to see nice flat bottoms. If we have 0 volts at any time looking at CAN with the key on, we don't want to ever see 0 volts. That's a short to ground. We could see one line stuck at ground. We could see just a quick little glitch that just drops down to ground. That's a possibility as well. That would indicate that line is shorting to ground. And it could just be one module that's doing that as well. I don't want to see any noise. If I saw, say, maybe it looked like a lot of static, a lot of ups and downs, and maybe it looked like an audio wave, if you've ever seen that, where it goes up and down a lot, that would indicate high RF noise in the pattern, and that would be a bad thing too. So that can cause interference in between. We can't always necessarily get that signal right at the DLC. It's the best place to test, but oftentimes it could be also internally in the network in the car too. So where would I need to go for that? So a good example of where we might go for that is our shop information. Right, so if you have a Varus or a Zeus or one of the Windows-based tools, I don't know why my password is now, but that's okay. It will load the vehicle. It'll load me into my information system. If I have Shopkey Pro or Mitchell Pro Demand, it will load me in there. It will give me my options, and I can look at the vehicle. And where I like to go for my wiring diagrams is we could look up the computer. We could look up CAN, but if we go into wiring diagrams and we pull up our computer data lines, because all of the wiring diagram categories are identical. So we'll go to computer data lines. Then we'll pull up my computer data line circuit. So it looks like there's 2 pages for this. So I can just click on here. And it will pull up my circuit. So we can see here's the data link connector over there. Let me zoom in a smidge. All right, so that's my OBD-II socket, as they call it. So it looks like pin 3 and 11. That's one circuit. We got 8 and must be 8 and 12, right? And then we got 14 and 6, right? So 14 and 6 mean CAN. So 14 and 6 go into this junction box under the right side of the dash. From this junction box, it goes in, and then it would translate all of the different signals. So this is basically our gateway here. It would translate the signals to the other parts of the vehicle. Looks like we have a couple loops in here. So those are probably those 120 ohm resistors on the end of open lines for the network. We could also check and see, well, what about this junction box? So it's highlighted there in blue. So I can just click on that from the wiring diagram, and it should do, oh, I got to give it some extra information here, I guess. So I'll call it a coupe. Okay, there we go. It wants to know whether it's a coop or not. Okay, there we go. That's better. So there we go. Okay. So are there TSBs related to this junction box? What are my top repairs, causes and fixes, specifications? How about my location? Where's that? So I can click on component location right from the wiring diagram, and then it pulls up any of my electronics for that junction box. All right, so I can pull that up right from here, and it gives me all that information right from the wiring diagram, right? So being able to check through a wiring diagram to see how is this vehicle wired, because if I had a communication problem here, we see everything goes in there first. So I'd want to check in this junction box first, and then I can also have a testing point for any of my other modules on the vehicle. So that just makes it a little easier to test. All right, so that is our week 1 of networking. Let's go and talk about week 2 of networking. So next week, we'll be continuing this discussion, and we'll be sticking to the 2-wire network. So we'll do a little recap on CAN, and then we'll go through FlexRay, which is pretty much just an advanced version of CAN. We'll go with MOST, which is a media-oriented systems transport. It's actually what that stands for. So that's media involved. And then talk a bit about Ethernet, which is an emerging technology in the last 4 or 5 years there on some vehicles. So we'll talk about that as well. So next week, same time, same place, 6 and 8 p.m. Eastern on Tuesday, Wednesday, 1 p.m. Eastern. And then on, as we're doing right now, our session 2 on Tuesdays gets live streamed to YouTube as well. When the live stream's over, that video is always available to watch at any time in the future. So if you are watching us on YouTube and you like the content, please make sure you thumbs up, subscribe, ring the bell in order to get notifications for the next time we go live. With that, let me get to questions. And while I'm taking questions, let me look at this. So this is this website that we have up here on the screen. This is your one-stop shop for any of our live online training that we've been doing. So including these classes that are available, you can register there. Also, we have what we're calling our new customer onboarding type classes. So these are everything from setting up your Wi-Fi. How about setting up your free Snap-on Cloud account in order to share vehicle reports and screenshots, etc. All the way through a standard diagnostic workflow procedure, everything from scanning the codes through, how we verify that our fix is there. So walks through all aspects of the tool. Mondays, we talk about the Apollo D9. My friend Al McCaskey hosts these class. So Mondays, Apollo D9, Wednesdays are Zeus, and Thursdays are Triton D8. Also on the Zeus and the Triton D8 days, Al talks through a bit of guided component testing as well at a high level. So the Apollo class is about an hour, and the Zeus and Triton class are about an hour and 45 minutes, give or take, because those have the extra guided component test aspect to them. So with that, I don't see anything in the live chat on YouTube. So let me look up in Q&A, and this is going to take me a second to read here. So let's see. Okay, so that seems more like a comment from Matt than a question, but on a 2015 Mitsubishi Outlander, get into the body control modules and be able to change headlights change coming on. Lots of different setting changes available inside the Zeus. Yeah, so thanks for that comment. Definitely, there is so much subject matter that I could talk about on any of these tools, especially with how these cars are nowadays and programming and changing settings in there and coding and all that. I think actually we might do a class on programming and coding and the differences and such as that. But definitely thanks for that feedback. Thanks for that input, Matt. And I know I appreciate you attending all these classes. I see you in here every week, so definitely appreciate that as well. So thanks for that. With that, I do not see any additional questions in here. I'm going to give you another minute or so just to type them in if you do have them. I'll just give you a little bit of time because I know I'm not the fastest typer in the world either. So I'll give you a little bit. And definitely make sure you check out our website, snapon.com/NOT. And also, if you're on YouTube, like, subscribe, hit the bell. All right. With that, I guess that is it. So appreciate all attending. Everyone have a wonderful rest of your week, however much you have left. And for those veterans with us, tomorrow's Veterans Day. So definitely appreciate your service. And thank you for looking out for our country, right? So with that.